So in this module, we're going to be looking at quantum physics. But before we do so, we need to understand the concept of photons. Now, we've previously looked at how energy can be represented in the form of a wave, and we know that light can be represented by a wave, and we've seen how light acts as a wave, such as through diffraction and single slit experiments, double slit experiments, etc. Well, there's another way that we can interpret light and other EM waves, and that is through the concept of photons. So previously, we've been introduced to the wave energy, and this can be almost denoted by a continuous flow of energy. Waves are just a continuous stream. But this new concept of photons, instead of describing energy in terms of a continuous flow, we're now going to talk about discrete packets of energy. And what that means is each individual photon continues a specific value of energy. So let's look at what the energy of these photons are relying on. So here I've got a list of all the EM waves, and it has the lowest frequency on the right hand side and maximum frequency on the left hand side. So as you go towards the left, the frequency increases. Now, photons that have a higher frequency have a greater energy. If this circle depicts the energy of each photon, you can see that as the frequency of the photon gets smaller, so does the energy. And the reverse can be said about the wavelength. If the wavelength increases, the energy that these photons have decreases. So we can therefore say that energy is directly proportional to the frequency. And this means we can change this directly proportional sign into an equal sign simply by adding a constant. And in this case, the constant is denoted by this h. And this h stands for Planck's constant. And it has a value of 6.63 times 10 to the minus 34. And photons are basically ways that we can represent EM waves in particular. And we know that all EM waves travel at the speed of light. So we can say that the frequency is equal to the speed of light over the wavelength. And if you plug that into this equation, we can also get that the energy of each photon is equal to hc over lambda. Now this means that if we were given the frequency or the wavelength of a photon, we could calculate its energy. And vice versa, if we had the energy of a photon, we would be able to calculate the frequency or the wavelength. When talking about energy, the unit we typically use is joules. But when it comes to photons, the joule is very, very large. So we have to introduce a new unit called the electron volt. Let's look at an equation that we all know, E is equal to QV. So let's say we applied a voltage of 1 volt across the electron. The energy of this electron would therefore just be equal to Q times 1. And where Q is the charge of the electron. So the energy will be equal to 1 times Q, which is equal to 1 times the charge of the electron is 1.6 times 10 to the minus 19 coulombs. So the energy carried by this electron is 1.6 times 10 to the minus 19 joules. So we can now establish that this energy here, 1.6 times 10 to the minus 19 joules, is equal to 1 electron volt. This is a new unit that we're going to use for our calculations. So when converting between electron volts and joules, 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. And this is a conversion that you will need to know for your exam. The definition of an electron volt is the energy of an electron when the potential difference across it is 1 volt. Now, the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.